Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Chung-0316 University. This is my name in Chinese, Chung-0316. Welcome to the course Seismic Evaluation and Retrofit of Structures, Lecture 3-1, over at the Department of Construction Engineering, National Taiwan University of Science and Technology. This is the lecture on Preliminary Evaluation 2-2. In the previous lecture, we talked about seismic demand, but it has not been completed yet. Today, we will continue with seismic demand in this lecture. And this is the seismic demand of a building equal to I times SAD divided by FU multiplication times W. In the previous lecture, we have already talked about importance factor I, in Chinese II-2 fundamental vibration period T, in Chinese 基本振动周期 total dead load W, 全部进载中 in Chinese, design horizontal acceleration response spectrum SAD, in Chinese 设计水平加速度反应谱. So far we have talked about I, SAD, and W, and the fundamental vibration period is used to compute SAD, the design spectral acceleration. And in this lecture, we will focus on FU, the seismic force reduction factor for structural system, FU, due to ductility. From Seismic Design Code Equation 2-15, we have an equation for the computation of seismic force reduction factor for structural system, FU, due to ductility. Seismic force reduction factor for structural system, FU, depends on two parameters. One is fundamental vibration period T here. This is the fundamental vibration period of the building. Another parameter is the allowable ductility capacity, RA. Therefore, once we have the structural vibration period T and the allowable ductility capacity, from this equation, we can have the seismic reduction factor for structural system, FU, due to ductility. From this equation, we can plot the graph here, shows the relationship between the reduction factor FU and the fundamental vibration period T. The curve is divided into 4 segments. The first segment from 0 to 0.2 T0D, and FU increases from 1 to square root 2RA minus 1. And the second segment is from 0.2 T0D to 0.6 T0D, and FU is constant, equal to square root of 2RA minus 1. And in the range from 0.6 to T0D to T0D, FU increases from square root of 2RA minus 1 to RA. And when T is larger than or equal to T0D, FU is constant again, equal to RA, the allowable ductility capacity. And from the curve here, the longer the period, the larger the reduction factor, because FU is in the denominator for the computation of the seismic demand. Therefore, the larger the reduction factor, the more reduction for the seismic demand. When the vibration period is very, very short, close to 0, that means that the structure is so rigid. There's no deformation under earthquake because the structure is so rigid. Even though the structure may have may possess ductility, but without deformation, ductility cannot be fully developed. Therefore, the reduction factor Fu is close to 1, no reduction for seismic demand. Therefore, when T equal to 0, Fu equal to 1, no reduction for the seismic demand. When the vibration period is very, very long, the structure is so flexible so that ductility can be fully developed, and the reduction factor Fu is close to Ra. Ra is the allowable ductility capacity, and we have maximum reduction for seismic demand. The higher the allowable ductility capacity Ra, the higher the value of seismic force reduction factor. Since the allowable capacity becomes higher, the structure has better ductility, so that we have larger reduction factor and larger reduction for the seismic demand. When the allowable ductility capacity Ra equals 1, that means that the structure has no ductility, and the reduction factor Fu equals to 1 and no reduction for seismic demand. When R equal to 1, square root of 2Ra minus 1 equal to 1. When Ra equal to 1, it becomes a straight line, a horizontal line. That means that Fu is constant and equal to 1. When Ra equal to 1, that means that there's no ductility in the structure. Therefore, no reduction for the seismic demand, and Fu equal to 1. And how do we compute allowable ductility capacity? From our seismic design code equation 213, Ra equal to 1 plus R minus 1 divided by 1.5 for site class 1, 2, or 3. From seismic design code equation 2-14, Ra equal to 1 plus R minus 1 divided by 2.0 for Taipei Basin. R is the ductility capacity of the building. For site class 1, 2, or 3, only 2/3 of the plastic displacement is allowable. Therefore, Ra equal to 1 plus R minus 1 divided by 1.5, that's 2/3. And Taipei Basin, for Taipei Basin, only half of the plastic moment is allowed because of basin effect. The duration of the earthquake record becomes longer in Taipei Basin. Therefore, in Taipei Basin, the allowable ductility capacity Ra equal to 1 plus R minus 1 divided by 2, and R here is the ductility capacity of the building. For site class 1, 2, or 3, only 2/3 of the plastic moment is allowable, so that the allowable displacement equal to delta A is the allowable displacement equal to delta Y. Delta Y is the plastic moment, plastic displacement, plus 2/3 delta U minus delta Y. Delta U is the ultimate displacement, and delta Y is the yielding displacement. That means that from delta Y to delta U is a plastic displacement. And if we divide the whole equation by delta Y, so that delta A divided by delta Y equal to 1 plus 2/3 delta U divided by delta Y minus 1. Therefore implies Ra equal to 1 plus R minus 1 divided by 1.5. In Taipei Basin, only 1/2 of the plastic moment is allowable, so that the allowable displacement delta A equal to delta Y. Delta Y is the elastic displacement, plus delta U minus delta Y is the plastic displacement, and then times 1/2, and divide the whole equation by delta Y, so that we can have delta A equal to divided by delta Y equal to Ra, delta Y divided by delta Y equal to 1, and delta U divided by delta Y equal to R. Therefore, we have Ra equal to 1 plus R minus 1 divided by 2. And R is the ductility capacity equal to the ratio of ultimate displacement to yielding displacement. And the curve here is the force displacement relationship of a building under earthquake, and it can be simplified as a elastic perfect plastic relationship. And the ductility capacity R equal to delta Y divided by delta U divided by delta Y, and delta U is the ultimate displacement, and delta Y is the equivalent yielding displacement. For site class 1, 2, or 3, Ra allowable ductility capacity equal to 1 plus R minus 1 divided by 1.5. For type A basin, the allowable ductility capacity Ra equal to 1 plus R minus 1 divided by 2. And this figure is taken from the Seismic Design Code, figure C2-1. For existing school building, the ductility capacity is assigned to be R equal to 2.8. That's 70% of the new one. For new school building, for newly constructed school building, R can be as high as 4.0. Therefore, for the existing building, the ductility capacity is smaller, only 70% of the new one. When T lies between 0.2 T0D to 0.6 T0D, Fu equal to square root 2Ra minus 1. And how do we come up with this value? For short period structure, the criteria of equal energy exists. Given two structures, one is elastic structure, one is inelastic structure. Under the criteria of equal energy, the energy possessed by elastic structure is the same as the energy possessed by the inelastic structure. For the elastic structure, VE is the seismic force for elastic structure, and delta E is the maximum displacement of the elastic structure under earthquake. And for the inelastic structure, the maximum seismic force is Vy, and the maximum displacement is Ra times delta Y. For the elastic structure, the energy possessed by the structure is the area of the triangle here, equal to 1/2. Ve is the height of the triangle, and delta E is the base of the triangle. And for the inelastic structure, the energy possessed by the structure is the area of this trapezoid, equal to 1/2 times the height. Height is Vy, times the summation of the top base. Top base equal to Ra delta Y minus Vy, minus delta Y. That's the length of the top base, and plus the length of the bottom base, equal to Ra delta Y. And then 1/2 and 1/2 cancel out each other. And you remove delta Y to the right hand side of the equation and delta Y to the left hand side of the equation. We move Vy to the right hand side of the equation and delta Y to the left hand side of the equation. Then we have Ve divided by Vy squared equal to 1Ra, 2Ra, 2Ra minus 1. Therefore, we have Ve divided by Vy equal to square root of Ra minus 1. Therefore, the ratio of seismic force of the elastic structure to the inelastic structure equal to square root of 2Ra minus 1. If the structure is inelastic, or if we allow the structure to be nonlinear, to enter into inelastic range, then we have lower seismic force. Therefore, VE divided by VY equal to square root 2RA minus 1, so that the seismic force of the structure can be reduced by 1 over Fu, and Fu equal to 2RA minus 1. This is the illustration why we have the value square root of 2RA minus 1. When the vibration period T is larger than or equal to T0D, and T0D is the corner period between short and medium to long period, and Fu equal to RA. And how do we have this value RA? How do we have this characteristic? For long period structure, the criteria of equal displacement exists. Therefore, if we have two structures, one is elastic structure and one is inelastic structure under the same earthquake, they have the same displacement. Therefore, delta E is the displacement, maximum displacement of elastic structure, and RA delta Y is the displacement, maximum displacement of inelastic structure, and these two are equal. Therefore, we have RA delta Y, the maximum displacement of the inelastic structure, equal to delta E, the maximum displacement of the elastic structure. And then from the similarity of triangle, delta E equal to VE divided by VY times delta Y. And then if we move delta Y to the left-hand side of the equation, so that we have VE divided by Vy equal to delta RA, and Fu equal to RA. If the structure remains elastic under earthquake, then the seismic force is as high as VE. And if the structure becomes inelastic under earthquake, the seismic force is reduced to Vy. Therefore, we have VE divided by Vy equal to RA. If inelastic behavior is allowed for the structure, so that the seismic force can be reduced by 1 over Fu, that's Fu equal to RA. And from seismic design code equation 2-2, we have the modification for the ratio SAD to Fu. If SAD divided by Fu is less than or equal to 0.3, no modification is necessary. If SAD divided by Fu is larger than or equal to 0.8, the ratio is reduced to 70%. Therefore, SAD divided by Fu modification equal to 0.7 SAD divided by Fu. When SAD divided by Fu lies between 0.3 and 0.8, linear interpolation is taken, so that we join the endpoints of these two segments. If we plot the equation into a curve, then we have three segments. One is when SAD divided by Fu is less than or equal to 0, that no modification is necessary. So the slope here is 1 to 1. When SAD divided by Fu is larger than 0.8, and it is reduced to 70%. Therefore, when SAD divided by Fu equal to 1, after modification, it becomes 0.7. When SAD divided by Fu equal to 0.8, after modification, it becomes 0.56. And then we join the endpoints of the two segments, so that we have the third segment here. So that SAD divided by Fu modification can be divided into three segments. The shorter the vibration period, the higher the spectral acceleration, SAD, from this curve. The shorter the vibration period, the higher the spectral acceleration. And then we go back to the curve here. The shorter the vibration period, the smaller Fu. That means that the denominator becomes smaller when the vibration period becomes shorter. Therefore, when the vibration period becomes shorter, SAD becomes larger and FU becomes smaller. Therefore, the ratio here becomes larger. And when the vibration period is short enough, the soil structure interaction may be more significant. Therefore, the ground intensity may be lower due to soil structure interaction, so that the ratio SAD divided by FU is modified and reduced. When the ratio is less than 0.3, no modification. When the ratio is larger than or equal to 0.8, it is reduced to 70%. And then in between, a straight line is joined two endpoints of the two corresponding segments. And here is a step-by-step procedure to determine seismic demand of a building. Step 1, from the usage of the building, look up section 2.8 of Seismic Design Code. Get importance factor I. I may be 1.0, 1.25, or 1.25, depends on the importance of the building. Step 2, measure the floor area from the dead load per unit floor area. This is given in advance, and then get the total dead load of the structure, W. And so far we have the importance I, and from the floor area we have the W, the total dead load of the structure. Step 3, measure the structural height, and from empirical formula we can have the approximate fundamental vibration period T. And the fundamental vibration period T is necessary for the calculation of SAD, special acceleration, FU, seismic force reduction factor. And then we move to step 4, from seismic zone, fault distance, site classification, and vibration period T. And then we can have the design special acceleration SAD here. Therefore, the structural vibration period is necessary for the calculation of the special acceleration SAD. And then move to step 5 and assign ductility capacity for the existing building, R. And from R and site class, whether it's site class 1, 2, or 3, or type A basin, according to equation 2-13 and 2-14, and then we can get the allowable ductility capacity, RA. And then from RA, the allowable ductility capacity and the vibration period T, according to equation 2-15 of the design codes, we can get the seismic force reduction factor FU here. From SAD divided by FU, the ratio of SAD to FU, according to equation 2-2 of the seismic design code, we can have the modification SAD divided by FU modification. Once we have the importance factor, W, the total dead load of the structure, SAD, special acceleration, FU, seismic force reduction factor, and SAD divided by FU modification, then we can compute the seismic demand of the building equal to I times SAD divided by FU modification times W. And here's an example. A building in Retrofit Elementary School. This is the front picture of the building. This is the rear picture of the building. And we are going to compute the seismic demand of the building equal to I times SAD divided by FU modification times W. This is the elevation of the building. This is the plan view of the building. And there are totally 14 columns C1 and 3 columns C2. And the dimension of C1 is 35 by 40 centimeters. And the dimension of C2, the cross-sectional area of C2, is 24 by 40 centimeters. Because this is an ordinary school building, the importance factor I equal to 1.25, because it is an is an ordinary school building. It is classified as Category 3. There's a building for public use with high occupant density. The building height, that's the roof elevation from the base, equal to 3.6 by 2, equal to 7.2 meter. And the fundamental vibration period along the corridor, because there are so many openings for the window, for the door. Therefore, T equal to 0.07 Hn to the power 3/4 equal to 0.07 times 7.2 to the power 3 divided by 4 equal to 0.308 second. And this equation is taken from the equation 210 of the seismic design codes. So far we have I equal to 1.25, and from the location of this building, there's a Yangmei Town at Taoyuan County. Then we can have the design special acceleration for the seismic zone for short period structure, SSD equal to 0.8 from table 2-1 of the seismic design code. Because there's no nearby faults, therefore the near fault adjustment factor for period with constant acceleration, NA equal to 1.0, and this is assumed to be site class 2, the amplification factor for periods with constant acceleration, FA equal to 1.1 from table 2.2a of the seismic design code. Once we have SSD 0.6, NA 1.0, FA 1.1, and we multiply all the three parameters together, then we have SDS equal to NA multiplied by FA, and then times SSD equal to 1.1 times 0.6 equal to 0.66 from equation 2-2.4 of the seismic design codes. So far we have importance factor I equal to 1.25, we have SDS equal to 0.66, and we are going to compute SD1 according to the location of the site at Yangmei Town of Taoyuan County. Then look up table 2.1, we can have the design special acceleration of seismic zone for 1 second period structure, S1D equal to 0.35, and we use 1 second period to represent medium to long period range. Because there's no nearby fault, therefore the near fault adjustment factor for periods with constant velocity, there's a mistake here, should be NV equal to 1.0, and because the site classification for the building is site class 2, therefore the amplification factor for period with constant velocity, FV equal to 1.4, by looking up the table 2.2b of the seismic design codes. Once we have S1D and V here, and FV, then we can multiply all the three together to come up with SD1, is the design special acceleration of the site for 1 second period structure. SD1 equal to 1.0 times 1.4 times 0.35 equal to 0.49 from the equation 2-2.7 of the seismic design codes. So far we have the importance factor I equal to 1.25, SDS equal to 0.66, and SD1 equal to 0.49. Then we can have T0D, the corner period between short period and medium to long period. T0D equal to SD1 divided by SDS equal to 0.49 divided by 0.66 equal to, I think there's a mistake here. It's a 0.742 second, 0.742 second, no mistake, that's okay. According to equation 2.8 of the seismic design code. And the fundamental vibration period T equal to 0.308 second. And it lies between 0.2 T0D and T0D. Therefore, the design special acceleration of the structure of the building, SAD equal to SDS equal to 0.66 according to table 2.5a of the seismic design code. Therefore, the structural vibration period lies between 0.2 T0D and T0D, so that the special acceleration is constant. Because the building locates as site class 2, therefore the allowable ductility capacity RA equal to 1 plus R minus 1 divided by 1.5 equal to 2.2 according to equation 2.13 of the seismic design code. And the fundamental vibration period T equal to 0.308 second lies between 0.2 T0D and 0.6 T0D, so that according to equation 2.15 of the seismic design code, we can have the seismic force reduction factor for the structural system due to ductility Fu equal to square root 2Ra minus 1 equal to 2 square root of 2 times 2.2 minus 1 equal to 1.844. So far we have I equal to 1.25, SAD equal to 0.66, and Fu equal to 1.844. And then we divide SAD by Fu equal to 0.3579, and it is larger than 0.3 and less than 0.8. Then according to equation 2.2 of the seismic design code, SAD divided by Fu modification equal to 0.52 SAD divided by Fu, 0.52 times 0.3579 plus 0.144 plus 0.144, and then after modification the ratio becomes 0.3301, which is less than the one before modification. Before modification, the ratio is 0.3579. After modification, it is reduced to 0.3301. So far, we have I equal to 1.25, SAD divided by Fu modification equal to 0.3301. And then we are going to compute the total dead load of the structure. The floor area of the roof and the second floor are equal. AF2 equal to A roof equal to 205 square meter. And the unit dead load, that's the dead load per unit floor area of the roof, is 750 kgf per meter square. And for the second floor, the unit dead load, that's the dead load per unit floor area, Wi equal to 900 kgf per meter square. From this information, we can calculate the total dead load, W, capital W, equal to small w2 times AF2 plus small w roof times A roof equal to 900 times 205 plus 750 times 205 equal to 338.3 ton force. So that we have I here, SAD divided by Fu modification, and W is just calculated, so that we can compute the seismic demand of the building. So far we have I importance factor equal to 1.25, modification of SAD divided by Fu equal to 0.3301, and the total dead load W equal to 338.3 ton force, so that we can calculate the seismic demand equal to I times SAD divided by FU multiplication times W equal to 1.25 times 0.3301 times 338.3 equal to 139.6 ton force. And here's the reference for this lecture. The first one, Seismic Design Code of Building, published in 2011 by the Ministry of Interior. Here's the link to download the Seismic Design Codes of Buildings. And the second one is Structural Concrete Design Codes, published in 2011 by the Ministry of Interior. Here is the link to download the Structural Concrete Design Codes. And here's the video for Lecture 3, Preliminary Evaluation 2. And this is the English version. And II-2, the English one, is under construction. It will be uploaded to the channel later. And this is the Chinese version. And here's the video for Lecture 2, English version, Chinese version. And video for Lecture 1-2, English version. There's no corresponding Chinese version for Lecture 1-2. And here's the video for Lecture 1-1. Here's English version, Chinese version. And in this lecture, we have completed the determination of seismic demand of a building. I equal to I times SAD divided by FU multiplication W. In order to calculate the seismic demand, we have to determine. We have the information about the importance factor I to indicate how important the building is. And then we have to know about the design special acceleration SAD, and SAD is calculated from the from the fundamental vibration period T. And then we should have seismic force reduction factor for structural system FU due to ductility. In order to compute the seismic reduction factor, we should have the information about the ductility capacity and the corresponding allowable ductility capacity RA. And all the video will be uploaded to this channel. That's all for this lecture. Thank you. See you next time. Bye-bye.